the rock speaks so eloquently of catastrophism and short timescales. Some deposits appear to have required longer periods of time or to have been deposited under calm conditions. Mudstones are among the most difficult rocks to explain by catastrophic processes. As in the case of the mudstone layers at Mam Tor, they are usually thought to have been laid down by the very slow settling of fine particles of clay in quiet water. Under turbulent conditions, mud gets stirred up and is only redeposited when tranquil conditions are resumed. Even then, the mud particles take a long time to settle out into layers. For this reason, it's been assumed that layers of mudstone, like these ones in Kimmeridge Bay in Dorset, must have taken thousands or even millions of years to be laid down. Furthermore, mudstones are very common rocks, comprising up to 3/4 of the entire sedimentary record. So this is a very significant problem for catastrophism. Once again, however, conventional thinking about mudstones is being challenged by recent research. Geologists have known for some time that fine mud particles have a tendency to clump together into fluffy or lumpy flakes about the size of sand grains. This process causes the mud to settle out of suspension much more rapidly than it would as individual mud particles. Laboratory experiments have now shown how this remarkable process allows mud to be transported and deposited quickly by flowing water currents. These experiments are causing many geologists to reconsider the conditions under which mudstones are thought to have been deposited. Mudstone layers like these in Dorset were probably formed rapidly in stormy conditions and not slowly in quiet water as many geologists have assumed. Another type of sediment that seems difficult to explain by catastrophic deposition is chalk. Chalk is a soft and often crumbly limestone composed of the remains of billions of tiny marine creatures. Under a high-powered microscope, the countless tiny particles that make up the chalk can be clearly seen. These tiny particles once made up the shell-like structures of microscopic algae. Similar algae can be found living in the surface waters of our oceans today. Over time, these shell-like structures typically fall apart to produce fragments which sink slowly through the water and build up as a kind of chalky ooze on the sea floor. Most geologists think that the great thicknesses of chalk, like these seen on the south coast of England, accumulated very slowly in just this fashion. Based on current rates of accumulation, it would take about 100,000 years for 3 feet of chalk to build up. If similar rates applied in the past, very long periods of time would be required to form the hundreds of feet of chalk that we see in the geological record. But there are some problems with the standard theory of chalk formation. For example, modern chalky sediments tend to build up in the very deep ocean. But there's abundant evidence that the ancient chalk was laid down in shallow water. Furthermore, the ancient chalk is very pure. It's composed almost entirely of shelly material, with very little mixture of other sediments. If it was laid down slowly over millions of years, it's hard to see how mud or sand could have been prevented from being washed in and mixed with it. These facts cause us to question whether the slow accumulation of chalk ooze in the deep ocean is really a good model for understanding how the chalk beds of the geological record were laid down. Could large amounts of chalk have built up quickly in the past? Given suitable conditions, the answer seems to be yes. Recent studies have shown that the concentration of marine algae in seawater increases dramatically under the right conditions of turbulence, nutrients, and temperature. The chemistry of the seawater is also significant, with rapid population growth rates more likely when calcium concentrations are high. Blooms of marine algae have been known to turn the oceans milky white and can be so massive that they are detectable from space. It is quite conceivable that intense blooms could have been generated during catastrophic events in Earth history, resulting in the rapid production of large amounts of chalk. In fact, rapid deposition would explain why the chalk layers in the geological record are so pure. There simply wasn't enough time for other sediments to get mixed in. There is also growing evidence that the ancient chalk sea was far from calm and placid. Many of the fossils in the chalk must have been rapidly buried in order to account for their excellent preservation. The chalk is sometimes piled into great heaps and banks over 150 feet high, indicating the activity of strong currents. And layers of volcanic ash within the chalk demonstrate that explosive volcanic eruptions were happening at the same time. These thin clay layers in the chalk at Peacehaven, East Sussex, for example, have recently been shown by chemical analysis to be volcanic ash layers. The chalk is an extraordinary rock formation, which has no obvious parallel today. It's now time to go back to where we began, to ask